Hello again. We've talked about common forms of radioactive decay. Now I want to spend a little time just thinking about decay in terms of energy, and in particular nuclear fission, as this particular decay finds worldwide use in energy generation, and despite its problems, it does not produce carbon dioxide. Let's start with how nuclei contain energy. The particles of the nucleus are protons and neutrons. Collectively, these types of particles are known as nucleons. There are two types of force at play here. All nucleons are held together by the strong nuclear force. This is a very strong force. It is always attractive, but it is very short range, about the size of a nucleus. The other force at work here is the electrostatic interaction. This one is really working in the opposite sense. The positively charged protons repel each other. The more protons you have in the nucleus, the more repulsion there is. The internal energy of the nucleus depends upon the balance between these forces, and that depends upon the number of protons and neutrons that are present. This plot shows an average energy per nucleus for different nuclides. It's at a maximum for elements with about 60 nucleons, meaning that the energy is gained, or I should say released, when we combine lighter nuclei to form heavier ones. This is nuclear fusion, and it includes the conversion of hydrogen to helium, the process that powers our sun. On the other side, energy can be released if we take a heavy nucleus and break it into smaller ones. This is nuclear fission, and can be important for some isotopes of some elements at the end of the periodic table, where the huge size of the repulsive electrostatic potential means that atoms can be more easily split. In other words, it's important for some actinide elements. There are a number of terms that we shall use when talking about nuclear fission that have important but slightly different meanings. We'll look at these now. The first term is the concept of spontaneous fission. Spontaneous fission is the process where a nucleus just breaks into two fragments. It is usually quite a rare process. The isotope of uranium most widely used in nuclear power production is uranium-235. Under normal conditions, uranium-235 decays by emitting an alpha particle and transmuting into thorium-231. But occasionally, that is not how uranium-235 decays. In fact, about once in every 5 million decays, the uranium-235 nucleus fragments into two new elements. These are called daughter nuclei. Now, because the neutron-proton ratio of stable nuclei increases with increasing atomic number, the daughter products need fewer neutrons. So we find that some of the excess neutrons are emitted in the decay process. And the excess energy? Well, that becomes the kinetic energy of all the decay products, which, after many collisions, becomes heat. This process releases a lot of energy, and it also forms new and usually radioactive daughter atoms, as well as directly releasing radiation. It will turn out that as well as showing an ability to undergo spontaneous fission, uranium-235 is also fissionable, meaning it can be induced to undergo a fission reaction. The most common way to induce nuclear fission is by neutron capture, and this can only happen if there is some source of neutrons. It doesn't just happen spontaneously. Normally we are not bathing in a sea of neutrons. They are not common products of nuclear decay, and they are unstable, if not bound in a nucleus, with a half-life of only 10 minutes. When a neutron does strike a nucleus, it may be scattered elastically or inelastically, but it may also be absorbed, increasing the mass of an isotope by 1 atomic mass unit. The probability of absorption depends on the nuclide, and the energy, meaning velocity, of the neutron. In some cases, as in the case of uranium-235, a neutron, bringing enough energy with it, will momentarily form uranium-236, which will then undergo a nuclear fission, producing daughter products and excess neutrons. This is effectively a catalytic process, but with each step, more of the catalytic neutrons are being produced. Now, a word about the fission of the nuclei itself. Uranium-235, with 92 protons and 143 neutrons, has many ways in which it could fragment. Indeed, we observe very many different fission products. But the fracture is not random, and it is not symmetric. It always splits the atom into just two products, and it is always an asymmetric cleavage, with one daughter having a mass of about 90 and the other about 140 atomic mass units. You may also hear about fissile materials. This is not the same as a fissionable isotope. A fissile material is one that can support or sustain a chain reaction. Now, I never thought I'd be making this sort of analogy, but what is involved in sustaining a nuclear chain reaction is rather like how a virus may be sustained in a population. With coronavirus, you have all heard of the R value. This is the average number of individuals that an infected individual will infect. If R equals 1, the average infected person will pass the disease on to one other person. The disease will propagate through the population with a constant number of people being infected. If R is less than 1, the chains of infection will become broken and the disease will die out. If R is greater than 1, we face an exponential growth in the number of infected people. R is sensitive to many things, not least what proportion of the population has been previously infected. So by our analogy, each person is a uranium-235 atom, and having the disease is the process of fission, and the virus equates to a neutron. So if on average more than one neutron from each fission event goes on to cause another fission event, we have uncontrollable exponential increase in the fission throughout the sample, and we've made a nuclear bomb. If the rate is on average only one neutron from a fission event catalyzes one more fission event, then we have a self-sustaining chain reaction, and we have a nuclear power plant. We can control the rate, the R value. To reduce it, we need more neutrons to miss other atoms. All we need to do is socially distance our fissionable atoms, move them further apart. And that's what we do. Uranium comes in rods, and in any single rod, mostly the neutrons escape from the rod without passing through too much fissile material. So the size and shape of a fissile material are important. Bringing rods closer together increases the rate. Moving them apart decreases the rate. We also use control rods. These are neutron absorbing materials that we insert in between the fuel rods. Control rods are analogous to the barriers of PPE in our pandemic world. I want to point out some examples where we use or see fission chain reactions. Obviously, it is the basis of nuclear power generation. So in all nuclear power stations we have rods of fissile materials, and we control the reaction by moving the rods or by inserting neutron barriers, control rods. We also use fission on a small scale, not to produce energy, but to produce neutrons for scientific experiments, just like the single rod reactor at the ILL, which is the European neutron source in Grenoble. And then if you want to exploit the exponential nature of a chain reaction and release all the energy at once, well then you've got a weapon of mass destruction. We normally think about nuclear fission and these neutron catalyzed chain reactions as a man-made thing. But actually, in 1972 in the Gabon, we discovered an entirely natural nuclear reactor, albeit long since finished reacting. What had happened was that hydrothermal deposition of uranium-containing minerals which had been driven by some nearby volcanic activity, resulted in sufficiently concentrated samples of uranium-235, so large and so concentrated that it began and sustained a natural nuclear reaction deep underground. Okay, we've looked at spontaneous fission, we've looked at the term fissionable and fissile materials. I need to tell you about fertile isotopes. So thorium, as we saw at the beginning, is exclusively thorium-232. It is a monoisotopic element. It is not a fissionable isotope. However, it can be readily converted into one. We call such a nuclide a fertile isotope. In this case, thorium-232 readily absorbs a neutron to become thorium-233. Thorium-233 is quite unstable and decays in a matter of minutes into protactinium-233 via beta decay. Protactinium-233 is also not stable, and it takes a little longer, but just a matter of days, to be converted into uranium-233, again by beta decay. Well, uranium-233 is fissionable and can be fissile. There's much current research in this area, but it seems likely that there will be many new thorium-based nuclear power plants coming online soon. This has a number of clear advantages over a dependence upon uranium-based nuclear power. Firstly, we have huge stockpiles of thorium. It's weakly radioactive, meaning these days it has relatively few uses. It's often deposited differently to uranium, so there's more diversity in its supply. All natural thorium is thorium-232. Unlike uranium, which is naturally less than 1% the isotope that is needed for fission. So no need for difficult and expensive isotopic enrichment. Also, the extra steps needed to obtain the fissile nuclide mean that there is no way to weaponize this nuclear material. Because thorium and uranium have long-lived isotopes, they form a bottleneck in any decay chain. Consequently, they are relatively abundant on Earth and can be easily mined. But because their chemistry is quite different, they form different mineral structures and so are often deposited in different places. Thorium is often present in monazite, which is the principal ore for the lanthanide elements. In fact, thorium is often seen as an unwanted byproduct of lanthanide extraction. The principal ore for uranium is the oxide uraninite. It and other uranium-containing minerals are often referred to generally as pitchblende. The main demand for uranium is for nuclear power, but only uranium-235 is potentially fissionable. Unfortunately, this isotope makes up less than 1% of naturally occurring uranium, and so in order to get a material that is fissile, this isotope must be concentrated, and that is technically challenging. Okay, this data is a little bit older, but the picture has not changed. Not all countries have economically viable uranium deposits. So in reality, just a few nations mine and process uranium. The geopolitics can influence availability. I've experienced this at the European neutron source when an old fuel rod was not replaced, as it was contracted to do by the Russians. The consequence here was a longer shutdown, and if I remember correctly, eventually a resupply from Canada. I'm just going to make a couple more connections between radioactive isotopes and energy. Normally we tell you that all energy received by the Earth comes from the Sun. Actually, that's not strictly true. The Earth itself produces between 30 and 40 terawatts of energy. What's a terawatt? 1 terawatt is 10 to the power 12 watts. A kettle is a kilowatt, so this is a billion kettles. Maybe it's better to compare with the energy from sunlight. The Earth receives 174 petawatts from the Sun, so our terawatts are much less than that. So it's not a huge amount, but it is something, and we think it's enough to keep the core hot and the outer core molten, which has massive consequences, such as creating the Earth's magnetosphere, which protects the biosphere from harmful radiation. And the convection in the outer core Well, that drives plate tectonics. Where does the energy come from? The answer is radioactive decay. The thorium, uranium and potassium-40 account for 24 terawatts. Okay, so this is not fission, it's more conventional decay mechanisms, but still, the excess energy becomes kinetic energy of the decay products, which becomes heat, and our core is very well insulated. So next time you see a mountain or volcano, this is driven to a large extent by radioactive decay of the actinides deep inside the earth. If simple decay can provide power enough to make mountains, surely we can use it for more mundane applications. Of course we can. Small lumps of highly radioactive materials generate heat. Insulate them and they can get very hot. The plutonium here is red hot. Couple that with a thermoelectric device that converts a temperature gradient into electricity, and then you have a nuclear battery, a nuclear material producing, albeit indirectly, electricity. How long will it last? How long's the half-life? 10 years? 100 years? More? Of course, because of the hazardous nature of nuclear materials, you might not want to use them for domestic applications. But there are out-of-the-way, remote places where stable, long-lasting power is needed. Okay, that's enough about radiation, decay and energy for the moment. Thanks for watching.